Okay. So I've just become aware that apparently you folks can't actually see the cloud recording subtab under the Zoom tab on Canvas. So I will be posting the Kaltura links instead. If I can't fix that with some visibility settings. So apologies for that for those of you who wanted to actually go back and review the previous ones, but they are all there. Recordings are all there. They just apparently weren't student visible. So that'll get fixed post haste. A few other bits of logistics. So we will wrap up our review this week and then actually get on to the beginnings of some new material hopefully by the end of this week. We'll see exactly how long things run today versus Thursday. And so keep that in mind as you either pay attention or sleep because it's 9 o'clock in the morning, that we will actually be getting into new material fairly soon. Okay. So if you recall, pipeline MIPS processor. So MIPS was 1986 introduction. Pipelining, as with many things, IBM in the 60s, right? You can win at Clue for computer architecture by just saying IBM in the 1960s with the candlestick, right? Always be right. So this was actually sort of designed to be pipeline friendly. And if you recall, while RISC, the R in RISC does stand for reduced instruction set computer, as a contrast with the very, very, very diverse ISAs of contemporaries like the VAX from Digital Equipment Corporation. If you read some of the retrospectives from the folks at IBM and others who, and Bell Labs that were doing some of the early RISC work in the early 1980s, they sort of regret that they didn't go with regular for the R in the paradigm, because it actually gives you a lot more insight into what they were going for. Simplicity favors regularity, regularity favors implementation, et cetera. Okay, so you're willing to burn some pipeline stages that do nothing for some of your instructions to buy regularity because it makes implementing them and pipelining them easy. And to understand what the trade-offs that people were worried about here, if you look at the set of Intel processors, Intel being a CISC ISA, they were not pipelined until the 486. And it was not immediately clear how easy it was actually going to be to do that. Because Intel instructions have no regularity at all. They're really designed from the ground up for multi-cycle. So people were actually pretty impressed when they actually finally pipelined the 486. Some serious engineering required. Okay. Now, there are certainly some circuit questions here in terms of how many stages you want to do. That's very technology dependent, right? So if it's 1986, I can access I have the ability to actually put enough transistors on a chip that I could have some cache, right? So that my memory access there is an on-chip access, hopefully, right? You go back to the 1970s, this was definitely off-chip. I'm taking a bunch of cycles, its own little state machine. And indeed, if you're looking at the scales of things in mid-1980s, this being one cycle is reasonable. If you look at more modern designs, everything touching memory, whether it be iFetch or MEM, are multiple cycles, right? So fetch now usually takes 3 or 4 cycles because that's how long it takes to access your cache. Okay. But certainly this general model roughly is fine. Okay, and that waste is even though pipelining is a utilization metric, you win more from the regularity in the implementation and the ability to maintain the throughput and not have complex checks than you do by saying that, well, I could stop my instruction here. Yeah, don't complicate it, right? Don't complicate things. Okay, so again, pipelining is all about performance and performance via utilization. Again, pipelining as an idea long predates pipelining computers, IBM in the 60s, but pipelining in general, industrial engineering. Right, this is some Henry Ford stuff we're talking about here. This is not, no transistors required, right? If we have built a bunch of units that do some particular task, if we can keep all of them busy, we get more work done, right? So it's not too deep an idea. Now, the key difference, and we'll spend a fair bit of Thursday talking about, exactly how this plays out in practice. The key difference is if you're building cars, all of your dependencies in your pipeline are feed forward. right? One car does not have some dependence on what you're doing on some other car. It just has a dependence that, I can't, attach the frame until I've already built the chassis, right? So everything is forward in time. In programs, obviously, this is not the case. Instructions actually do depend on each other, okay? But ideally, you want to spend as much time as possible here in the steady state. And if I am executing trillions of instructions, then, the few cycles it takes to fill my pipeline, I mostly just ignore them, right? A few cycles at the end it takes to drain it, I mostly ignore it. And we really think about this as a throughput optimization, where in the steady state, we are doing one instruction per cycle, right? So pipelining ideally, if there are no other sources of stalls, and there are always other sources of stalls, but in your spherical cows homogeneously filled with milk floating in a frictionless void, view of pipelines, right? CPI 1, hit the Flynn limit, everyone's happy, clock cycle's high, life is beautiful. Okay. So how does it actually work well? So this is, again, sort of a design space question. What are properties that make pipelining easy? Again, regularity, regularity, regularity. So everything being the same length means that it's very simple to figure out that you have actually fetched an instruction and that you can then decode it. There are lots of jokes that, the x86 ISA is mostly limited as a market perspective by the fact that only 2 companies can build a working decoder. Right, the rest of it's pretty easy. There aren't a whole lot of instruction formats. And to the maximum degree possible, these instruction formats share fields. Right, so again, very simple to figure out what it is that I'm supposed to be getting out of my instruction memory, and then what it is that it actually is then asking me to do. The simpler and more regular that this is, that means I can get this caught on things and pull it out of my pocket. The simpler and more regular, still on? Okay, good. Simpler and regular that is to do, then you can actually directly wire some of these fields into operand sources and other pieces of the decoder infrastructure rather than having to go through tabular lookups. Again, this helps quite a bit. It is a load store architecture, as basically everything since the early mid-1980s has been, because memory is just too big and different and complicated and expensive compared to everything else. So I am not going to have an add instruction that can get its operands from either registers or memory and handle all the potential cases. I don't have to worry about my add having a cache miss. That's an x86 problem. Or in x86, your add can have a cache miss. So they're like, we're not dealing with that. Loads are loads, stores are stores, and keep it nice and simple. Okay. And similarly, each instruction is not going to do a whole lot of work. Right, so again, you look at a contrast, x86 has the call and return instructions, right? So the return instruction cleans up your stack for you, right? And returns control and, does some other things. Call instruction sets up your stack and. So it makes it very easy to implement, right? If you're not doing a whole lot of work per instruction, right? And there's some memory alignment stuff. When we come to caches, unaligned memory access is very cache unfriendly. Again, before you had enough transistors to fit a cache, you didn't really care, right? Because if you're going off chip to go to memory, then it was going to take forever anyway. But the number one reason is that it was designed to be pipeline, right? So make sure you do get your causality correct, right? MIPS does not happen to be pipeline friendly. Every single decision in the design of the ISA and its microarchitectural implementation was designed for pipelining from the ground up, because pipelining is the lowest overhead, highest return performance optimization that you can basically have in any sort of computer architecture, microarchitecture implementation, right? You want to keep all the transistors as busy as possible, as much of the time. Pipelining does exactly that. It's well known, well studied. And it doesn't cost a whole lot of extra transistors to do it. You're really just putting in a few additional state mechanisms to save intermediate state, which is relatively small in the grand scheme of things, right? And then you need to check for the various hazards. And so here, and I apologize for those of you who will be viewing this later, I'm going to do a little bit of board work. So I think the way we need to start thinking about, to get your head out of the FD, EMW mindset and just really start thinking about queues, right? Now let's not worry about exactly what's in each of these stages, or even not really worry about how many of them there even are, I have some set of queues. Now, in our basic pipeline design, each queue only has one element, so they're kind of degenerate queues, but still think of them as queues, right? So they are one wide and one deep. That is our degenerate queue, right? And so we have a queue of PCs. We have a queue of fetched instructions, right? We have a queue that now has local operands and control. We have a queue that has intermediate results and control and some additional operands. And then we have a queue that has results and control. Right, so it's sort of the structures of what's in each of these queues. And you can subdivide these further. And I want you to start thinking about, because we're going to start by next week, shifting this around a little bit, right? So what would it mean for this queue to get wider? What would it mean for this queue to get deeper, right? Would anything change, right? So again, if we have our assembly line model, right? Imagine a world of completely independent instructions, right? It's a very strange program. Maybe it's a busy loop doing nothing. I got a whole bunch of completely independent instructions. They're just going to walk, and all my dependencies are forward in time. Life is good. So think about where the loops in this design are. Everywhere that there are loops, that is where there is potential for pain and suffering, right? So I have a loop that feeds back from here to figure out whether or not I'm actually on the right path, right? And then I have loops that feed back from here for branch resolution. I have loops that feed back from here. If it's based on an intermediate result, loops that feed back from here, right? If I'm any of my forwarding loops, these are all going backwards in time, right? So I really want to start thinking about an abstract model. I have a queue, which is some width, some depth, and some number of backward arcs, right? And as long as you understand where some of these things are produced, you're good to go. And then you can adapt this to sort of any particular pipeline, however many stages and names it has. Now, to just give you an idea of where it might be reasonable to say, even in a very, very simple design here, without changing the semantics too much, here's one place that I could actually imagine increasing the depth of my queue, and it would be reasonable, right? So I could have here a queue of decoded instructions and the current value of their local operands. And the reason I can increase this depth is because I expect some of the stuff here to be thrown away, right? And I expect here there to be some stalls. So I can try to hide some of that latency by buffering, right? So think about your favorite video player, lots of buffering, right? Because it's outside of this particular loop, inside of these, I can't get around these, but I can decouple this front end that's fetching instructions, right? And it doesn't have any further dependence from things that are going even further down the line. If I've gotten to here, if I've passed this, right, then I already know that I'm on the right path. Right, so in your MIPS design, everything after branch resolution, right, is right path instructions. So I could decouple the potential instructions and the known instructions. I could decouple that with a queue. I could stall here, but here I could have more than one place to put something. I could still only have the hardware to do one thing at a time, but now I could overlap the fetching of additional instructions with, say, some cache miss, recover some of my penalties. So again, just start thinking about this in the back of your head. That this is the generalization of the current material we're here reviewing, even though we're talking about this 5-stage pipeline as our prototypical example pipeline. There's nothing magical about 5 stages, and we will rapidly, by Tuesday, be looking at some different tweaks that we're going to start doing. In particular, we're going to start playing around in this width dimension as we go to Technically, we don't really play around with that until we go to superscalar, but we're going to at least have to squint a bit as we go to VLIW. Okay. So again, 5-stage pipeline, nothing special, but think about it from the perspective, map that back to what's going on here. Right. So here are all the bits and pieces. Again, for the focus of this class, we don't really care too much about, oh, sign extension is here, it's built this way, it's in this stage. We really care more about this view. What is available at the end of each of these pipeline stages? Right? When do major events resolve? And I could just tell you that operand read occurred over 3 cycles, and you just know that they were done at the end of it. You wouldn't really have to figure out, how do I build a 3-cycle register file, right? That's not the point of this class. Right. We're just going to assume that having built one, you could, if necessary, build, some variants of this if you need to go a little further. We're going to try to generalize. Okay, so our control signals can be determined via decode, and by control here we mean not the control of instruction flow, but the control of what needs to be done to implement a particular operation, right? Because the goal of an instruction is to cause an operation to occur, right? Consume some operands, cause an operation to occur. So this at least tells you what the instruction actually asks you to do. We'll also have pushed all the branch stuff back here since it's just a simple comparison. All right, so you could graphically represent it like this. Right, you could ask questions, how many cycles it takes to execute this code. Again, if you're doing this sort of in the small, we often don't start from the right steady state, so it's a sort of an underperforming version. If we start from nothing, we start to have to fill the pipeline, but you can still get a pretty reasonable idea. If you want to think about things like steady state, imagine I've got some loop, right, and then look at how many cycles it takes on average to iterate. Don't worry about that startup on the first one. Okay. We can ask what the ALU is doing in cycle 4, and we can ask, are there hazards? Why does it occur? How are we going to resolve it? Right? Because again, if everything was feed forward, no hazards, but real things have hazards. Okay, and we're going to have to actually, in any real pipeline, make some modifications, because it turns out that not everything fits that nice simple 1986 paradigm. So multipliers are bigger and slower, right? So one option, I have a 2-cycle multiply, and I can have these stages in parallel, right? So that means that I could figure out that I'm doing a multiplication, send it through the multiplier, and its result will be ready here. Right? I have a register in the middle. You could do this as a multi-cycle path. You probably don't want to do a multi-cycle path, complicated from a circuit perspective, but just have a 2-stage multiplier, 4-stage, however many it needs, right? So you can overlap different functional units with different latencies, and then sort of to the degree that these don't stretch out your average instruction with lots and lots and lots of do nothing stages, right? If I had a 20-cycle multiplier, I probably don't want to do this, right? Because that means that all the rest of my instructions for regularity are going to sit there for 15 cycles doing nothing. Yes.
So if you don't make the clock twice as slow, will that run into it doesn't have the right operands or what?
So if the multiply is so slow that it would take a clock's if you want to sort of push this into the ALU and make it single cycle, right? Then you'd have to make it twice as slow. Otherwise it wouldn't. The operand flow would be fighting with each other on the wires. Yeah. Right, I mean, your critical path is your critical path. Can you do multi-cycle paths? If any of you are doing design automation, low-level design, yes, you can. Is this how they work? No, you don't do multi-cycle paths with pipelining this way. This is probably going to be pipelined here. Okay, so it's better to take 2 cycles because you've got the space in your pipeline. Again, I'd say even if it's, say, 4 cycles, it might not be too bad. Right, that additional waste is not enormous, but at some point there's going to be a point where you say, no, I'm going to need to special case it. I'm not going to put it in the pipeline with everything else if it's that much slower, right? So for instance, for divide, which is going to take 40 cycles, you don't do this, right? You don't stretch out your entire pipeline for divide for 40 cycles and make everyone else wait, because 3% of the time you execute a divide, not even 3%, right? Instead, use special case sets. So you always have the option to do something that breaks this paradigm and regularity, right? But if you can shove it in, you do. Okay. And of course, in real machines, right? A lot of these things are actually broken up into multiple cycles. They do take quite a while. So if you're looking at sort of a modern setup for even your L1 cache, right? You might be able to make your TLB small enough that you can do a TLB access in a single cycle. Your L1 cache is too big to actually do in a single cycle these days. It's going to be 3 or 4. And same for instruction fetch. Actually, for the Pentium 4, I think it was 4 cycles for instruction fetch. Again, how much you want to push the clock, how much the technology is going to let you do. So these things can be reasonably arbitrarily subdivided. Even the ALU can be subdivided to some degree. Yes.
Is there ever a reason why you make the clock twice as slow as opposed to lighting it cycles? Because if you were to make the clock as slow, you slow down everything.
Yeah, you slow down everything. Yeah. So the only reason you'd want to, so I can point you to a paper on selective depipelining, but it's purely an energy optimization. So there are some reasons for the purpose of energy. If you are willing to sacrifice throughput, you can make very deep complex operators. I can point you at the paper, but in the general case, it's not a good idea. There are specific cases where it's of interest. Okay. So again, to the degree you can break these up, you can pipeline memory to some reasonable degree. Not usually too much of a problem. Some things you can't pipeline too much further. As I mentioned, you get to the limits and you start to have entire clock cycles where you're just moving data from one part of the chip to the other. That's usually a sign that you have dug too deep and you're about to find a Balrog. That Balrog is going to melt your chip. That's actually basically what was happening. Okay, there are lots of other possibilities than this 5-stage pipeline. So again, you can think of all these as queues. They're going to have different feedback loops, different challenges, right? So old ARM v7 often only had 3 pipeline stages. So all of the backend, so all of the execution, all of the data memory access, everything, and the commit and the write back, all back here in one stage. These did not have very fast clocks, but that was okay because they were designed to be embedded processors running at a megahertz, and they were fine, right? So these are technology versus deployment trade-offs. Intel's Xscale was their own embedded piece there. A couple of instruction memory fetches, a couple of data memory cycles, right? ALUs are still fast. And we'll see some other examples as well a little later on as we go to, again, some alternative queue structures. We look at, say, some modern-ish superscalar designs. You'll see something with, say, like maybe 12-stage. Yeah. Okay. So as a reminder, again, why this doesn't all just solve all of our problems for now and forever, and we had to keep going further, and we didn't actually get to CPI1. We have structural, control, and data hazards. Now, again, if you are designing your ISA and its microarchitecture with pipelining in mind from the get-go, you will mostly get rid of your structural hazards at design time, right? So you'll mostly decide if I need 2 of something and I can afford to build them, I'll just build 2 of them and then I won't have a structural hazard, right? We'll see these come back when you have more dynamism in your schedule, right? So again, I said that these were queues and you probably assumed that they were FIFO, and so far they are. Later in the class, they won't be. Right, so some of these queues will start being a different type of beast entirely. They'll have their own priority schedule, and then you get some dynamism, and then, yeah, you don't actually know whether or not the resources are going to be available. Right? It will become worthwhile eventually to allow these to creep back in and just catch them when they happen. Data hazards, however, are going to happen all the time. Control hazards are going to happen all the time. Okay. All right, so these are mostly going to go away. We got to detect to dissolve it. So what's a structural hazard? If we only had one memory, then doing instruction fetch and doing your data access at the same time would be bad. That's okay. We have enough transistors. We'll have an I cache. We'll have a D cache. And there are some challenges that will occur here. Right. So for instance, if I am doing self-modifying code, I've got some instructions here in my iCache. I'm writing things here in my dcache. If for some reason I was actually writing the instruction that I was trying to read right here, logically, since everything clearly by the contract happens one instruction at a time to its completion, should already have been written, I should read the right thing here. With two separate memories, that's a little challenging. The answer to this that a number of ISAs came up with that were more modern was those aren't actually the semantics. You have to do an explicit flush, or else you have no reason to believe that anything in your instruction cache will actually have been updated by anything in your data cache. They're not actually explicitly synchronous. But Intel is an old ISA. So in Intel semantics, yeah, if I were to do a write here and a read here, I have to get the data I just wrote. Again, don't write self-modifying code. Actually, Intel's even worse. Intel allows not just for self-modifying code, but cross-modifying code to have the same semantics across multiple threads in the same program. But, design decisions sometimes come back to haunt you. But for everything that isn't self-modifying code, this is a beautiful, lovely, lovely fix. And in particular, it has some other benefits as well, which we'll see more when we talk more about caches, because this stream of accesses and this stream of accesses look very different, right? Your set of instruction behaviors and your set of data access behaviors have very different patterns, and so you can basically specialize the localities in each of them. Okay. So again, backwards in time is bad. We are not from Gallifrey. And, of course, after the last season, neither is anyone else, but what you're going to do. Forwards in time is fine. Yes.
Why are we able to have like a dependency going at the same exact time? Because no guarantee that.
So think about where our state is. Our state is in one of these registers, right? So if we're looking at something that is available in this cycle, right? So I have a data that I could write into this register file. I have a data that could be read from this register file. I can do bypass because the data is already ready in this cycle.
Oh.
Yeah, right. So in particular, if you look at the things that I can do with forwarding, right, all of my lines are vertical. In some particular cycle, an operand is available, and I can consume it. Yeah, I'm not drawing all the muxes. Yeah. And this doesn't actually tell you exactly what happened. This just tells you about, logically that this is a dependence that could be resolved because it's not backwards in time. Right? This doesn't tell you the forwarding is happening. I can't sort of throw things forward in time. Right? Everything happens in a clock cycle. Right? So all my lines ultimately are going to be vertical. Right? But these two I just can't fix at all. Right? If I actually need data here that isn't available until here, I'm just kind of hosed. Right? Forwarding can't fix that. The data is not available. Okay. So in this sort of pipeline, the one that we care about is read after write. We will start to care progressively more about its two friends that we will talk about on Thursday quite a bit. We can always just do nothing for a while, right? Every time that we actually have a dependence, we could just stop the world. We don't have to quite do that entirely, right? We can do a little bit better, right? Again, as soon as an intermediate value is available, right, we will forward them. Right. So again, think about the queues. Well, of course, I lost my chalk. There we go. Right. So if you look at when things are available, right. So here in this register, we have intermediate results from the ALU. Right. Those are available here. Right. Here we have all of our results are available, whether it's from the memory or the ALU. We have a copy lying around. Right? So in our 5-stage pipeline, there are only 2 places that results could be coming from. Again, in a 12, in a 20, in a 50-stage pipeline, there are, how should we say, more. But if it's available, I could use it. Right? Pretty straightforward. So again, this doesn't resolve things that are This resolves dependencies among instructions, but not things that are backwards in time because I haven't produced it yet. Okay. So now you have to think about the other side of it. When do I need it? Right, so in the 5-stage pipeline, at least, all I need here is a PC, right? What I need here is a fetched instruction, right? So this is my sort of decoupled front end. Doesn't really have a lot to do with the data flow, only the control. Right? I'm not dependent on data values too much. The only data value that I'd be dependent on is a computation affecting the PC, right? So for my jump register is affecting the PC, then that's how I get branch prediction, these sort of things, right? But for here, I need, if I'm doing branch resolution, I need my operands for branch, all the various flavors thereof. And here, if I'm going to use the ALU, I need my ALU operands. Here I need my memory operands, right? And here I don't need anything because everything's done, right? So if you want to, again, think about generalizing this, if I told you however many stages there were, if I just told you, here is the stage in which I need particular operands, here is the stage in which particular results are available, right? Even if what was in the middle was just some, J.J. Abrams mystery box rather than an ALU or a memory or what have you, it doesn't matter. You'd still understand how the schedule would work, right? So how do you fix this? Duct tape. I mean multiplexers. I mean duct tape. I mean multiplexers, right? They are the duct tape of computer hardware. So you just basically say, I'm going to do all of the possible places my data could come from. In my pipeline, that's not a whole lot of them, right? There are only 2 places that additional results are available, right? So every place that there is a consumer of an operand, I am now going to have a multiplexer across all the places there might be a live version of that. Again, for 5 stages, this isn't too bad, but think about the scaling that's going to happen when you go to 20, right? If I have, 8 places that this operand might be, that multiplexer at some point is going to start having a size and latency rivaling my adder that it's actually feeding. You're going to get some diminishing returns on your pipelining from all of those backwards loops and that you have to forward across. Okay, so if your data dependencies are still aligned such that the distance between the production and the reuse is at least as big as the difference between the number of pipeline stages in which the consumer and producer are living, then great, you can get back closer to that Flynn limit, right? And muxes as far as the eye can see. What's in the forwarding unit? Not much, just a bunch of Boolean logic. This just turns into some really simple operations on fairly small control operations, right? So each of these are register specifiers, only 5 bits each. You're looking at a couple of gates deep on 5-bit entities. This part is not too bad, right? Even though it seems like a bunch of if-else logic, I assure you this is actually pretty shallow and pretty small, right? And then again, of course, there are multiple places that could be producing the same name of something, so you need a little fix there. But again, we're not going to dwell on that particular in this class, right? Obviously, you want the most up-to-date version of your operand, right? If there are a bunch of instructions that have produced, some version of register 1, you want the one that would have been most recently produced before you would have logically executed. Okay, so you put it all together, and as you can see, mux trees, as far as the eye can see, a little more complicated. Everywhere that there is a backwards branch in this loop, complications. Okay, so everything uses pipelining, with a couple of very mild asterisks, right? It is a throughput optimization for instructions, which is a latency optimization for programs, because no one is terribly concerned about the latency of a single instruction. People are concerned about the latency of programs. Or even if you want to do smaller granularities, they're concerned about the latencies of tasks or phases or sort of human understandable logical pieces of programs, right, in some sort of larger software structure. So even though we are in fact actually increasing the latency slightly of individual instructions, no one's going to worry about a couple nanoseconds of additional startup delay, right? So again, in the same way you think about this series of queues and buffering, right? So yes, your video player does spend a couple of seconds at the beginning of your 2-hour movie doing some buffering, and you live with it because it makes your playback that much better from there on out. Here we're doing the same thing, but at an even larger scale, more zeros, right? We're burning a few nanoseconds of startup latency for that first instruction to get through for trillions of instructions worth of throughput. Okay. So the missing piece we have not reviewed yet is memory. So let's talk about our memory hierarchy. Right now, our memory hierarchy is actually deep and includes a bunch of things that aren't even memory. Right. So we're again thinking about how still mostly, at least at this point, looking from the logical representation with respect to a user space program from the ISA of some nice big flat, right, array of bytes. Right. If you look at how your program is specified, it says my memory is an enormous array of bytes. And depending on whether I'm a 32, 64, whatever bit machine, that's my approximation of infinity is 2 to the 32 or 2 to the 64, et cetera, bytes in this big flat array. But in reality, we obviously do not have 2 to the 64 bytes of addressable memory for every program of the 1,000 processes that are running on your modern machine physically available, right? So obviously, it'll look a little different in practice. So what you actually have is a hierarchy, right, where you're going to access the on-chip caches, main memory, and if main memory isn't even enough with virtualization, right, you might even go off into secondary or tertiary memory. Right. Does anyone know what some of the standards for tertiary memory still are? There's some ancient technology still in use today. Still actually used, right? So you go from SRAM to DRAM to SSDs to hard drives, and it's our favorite way to use rust on plastic. Thankfully, no, it's tape drives. Tape drives are still a thing because they're just that cheap. And they're just big archives of tape robots still out there. If you hit tape archive, you've lost, right? You've lost the memory game. But at that point, you might as well call someone to just go run a hard drive up and plug it in, right? It's about as fast. Sneaker nets actually also have been proposed. Okay. So the scale of this, well, okay, the scale of this picture is a little small. But these lines, as you can see, are on a log scale and moving apart from each other, and it hasn't gotten any better in the intervening additional decade. So if you're, again, looking at things where you're in a VAX 1980 model, i.e. the type of model that you were living in when you were designing an ISA like x86, when the relative performance of memory and core work were similar. And in fact, you could even argue that depending on your design point, memory might even have been faster than some of the stuff your core was doing. Again, if it's 1978, your computer is a series of boards with discrete components on them wired to each other, possibly by hand, right? This is not a single chip microprocessor at this point for anything particularly interesting. But by the time you get to single chip microprocessors where everything is integrated, and again, things are getting faster, but the ratio between them is diverging rapidly, right? So, if you look at this sort of as clocks per DRAM access, as your core gets faster and your memory gets faster, right? So your memory was getting faster at like 7% per year, and your clocks were getting faster at like 60. So, the difference between two exponentials is exponential, and this is what we call the memory wall, right? Which is that basically, right, we're not going to win by going to memory. We have to do something a little smarter. So again, even by the time that you're looking at 10 years ago, right, you're looking at several cycles per L1, 10-ish cycles for an L2, and tens of cycles for an L3. And then if you're looking for hundreds of cycles for main memory accesses, right? So again, we did the math the other day, right? If you were doing 5 gigahertz and it took you, 50 nanoseconds to access your memory, hundreds of cycles, and that's fairly optimistic to some degree. Okay. So this has not gotten better even as the clock cycles on chip. So these scale a little more reasonably because these are all built out of the same material, right? So these, when they change, it's either sort of very local technology shifts or it's a question of sizing, right? So the physical wire length issues and wire scaling versus tech scaling do affect these, right? So again, if you're looking at that, remember that picture of Zen 3. Some of your L3 is much further away than other parts of your L3. How many people have ever looked at the diagrams of intercore latencies on a Zen processor? How many people have ever been to a non-tech Tom's Hardware? How many people actually still read internet news about anything? Is it all TikTok videos now? I don't know. Sometimes it's hard to tell. Okay. So I'll pull in some, when we go back to caches later, I'll pull in some more modern numbers, but it doesn't really matter. The same idea is true, right? So a good memory hierarchy is going to try to hide as much of this as possible, right? Right. Physics doesn't like us. Large memories are slow, right? Speed of light is finite. Speed of electricity in copper is finite and slower than the speed of light in a vacuum. If you want a nice fast memory that's operating, it's got to be small because it has to be local. This also plays out from energy perspectives as well, but for a moment, we're going to mostly talk about performance. Okay, so the way that you fix this, or at least the way that you try to fix this, is caching. Now, an important thing about caching is that while pipelining is pretty much just universally good, caching is a heuristic that depends on behaviors of programs. Yes?
If large memory is a naturally slow investment for yourself, does that mean like a 1 terabyte flash drive is like significantly slower than a...
So at that scale, probably not. Because if you're looking at the physical sizing difference between those isn't actually too radically high. If you look at where most of your time is going, by the time you get out to an SSD, wire latencies, drivers, the actual chip latency. So actually, the right way to look at that within the SSD is the scaling of a single flash chip, and there are many flash chips within an SSD, is determined by its size. So a larger flash chip is going to be slower, but if I have 64 versus 128 independent flash chips, then modulo the additional routing cost of getting to the right one that has the data, the actual time to access the data on that particular chip, right, is no different if I have 64 or 128 of them.
So by size, do you mean like physical size or like storage size?
So they're strongly correlated, right? So certainly if I increase the physical capacity, I'm going to have a larger physical substrate in some dimensions. Depending on how those dimensions play out, I'll have different scaling factors. But whether or not the critical part is much slower or much faster depends on the organization of the memory, right? So if I wanted to have as a single flat chip 8 terabytes or 32 terabytes, right, I would have very, very radically different timings. Also, if I tried to build a single chip with 32 terabytes of memory, you don't try to do that. It's not a good idea. Your yield is going to be fairly silly. But internal organization, the individual chips you're building out of, they have their own sort of local scaling factors for driving the actual data. And the rest of it, you're looking at some network delay, right? So at some point, things grow by having a collection of things, right? And then your delay often ends up being, the chief overhead actually ends up being getting to the data rather than actually getting the data. Even really true to DRAM for a great extent as well. Okay, so, oops. Okay. So hierarchy and parallelism, right? So we're going to try to access things in parallel. We're going to try to impose some hierarchy. Now, this is going to be generally just a good idea. The hierarchy, again, is a heuristic, right? There are lots of applications which will get absolutely positively zero benefit from your entire cache system, right? So anyone think of an example of something which is canonically cache unfriendly? My AMAT, the caches, they do nothing. Yes. No, actually, it's generally going to be, well, okay, so yes, you could have something that uses no memory at all. Your busy loop doesn't care about the cache, but that is an interesting degenerate case. But we're looking for things where you want to have the cache as an optimization on memory and it fails. So whether you have a cache or not for the busy loop doesn't matter, but it doesn't fail in that sense. It just didn't do anything. Yes. Yeah. So canonically, the worst case for caching is streaming, right? So if I have two enormous vectors, so let's say I got a couple of 4 GB length vectors, and I want to stream them through my 64 kilobyte cache, and all I'm going to do is add up every element from these two vectors. Maybe I'm doing dot products. I'm going to multiply them together element wise and keep a running sum locally. If I never reuse data, then the fact that it happened at some point to live in my cache gives me absolutely positively, zero benefit. I will get some spatial locality at blockable transfer, but yeah, they're no fun. The other thing that works very poorly with cache heuristics are large indirection-based streams. So if rather than just running a data stream through everything, or at least I know that my next element have some pattern in memory. If I am walking an enormous graph, it's even worse, right? So if I am walking an enormous pointer-based structure, not only will I have no temporal locality if I don't actually ever hit the same node again, right? So imagine instead of a big array, I had a big linked list, right? Now it's even worse because I touch every element once, but where the next element is arbitrary, and I have no way to necessarily predict it, right? So there's certainly things there where caches don't work, but we make the common case fast. Most things that humans write have some level of locality, and we're going to exploit it, right? So this is a reaction to the way that we actually happen to solve problems. It is not some foundational truth about how we should spend all of our transistors, which is again one of the reasons why you get trade-offs, right? So if I decide I want to build an accelerator or I want to build a better L3, depending on my workload, right? One of these may be a much better decision than the other. Okay. So there's some other interesting things that actually happen here sort of indirectly. So you'll note that your ISA, with the exception of some things like SIMD instructions, is effectively scalar, right? When I load something from memory, I load one word or one byte, right? But if I bother to go out to memory, even through the cache, it's one-dimensional, right? You have cache blocks. I have aggregate transfer sizes that are much larger than my access size, right? So I'm not going to bother to do anything less than 32 or 64 bytes, right? There's really no point. Here, it might be a little bit larger. Here might be maybe 256 bytes. I can get all the way out to page level transfers of disk sectors. So pick your favorite multiple of 512 bytes, usually 4K, but could be larger. So if you're going to go further and further away, you bother to bring more and more stuff, right? This is a pretty obvious analogies to how you run things in your own life. If you're going to bother to go to Harrisburg and go to Costco, right? You're not taking the Mini Cooper, you're taking the truck, right? So if you have to take a long trip to do it, you're going to bring back as much stuff as you possibly can. Same sort of logic is at play here, right? Okay, how these things are organized: inclusive, non-inclusive, exclusive. There are some different models. This will become much more interesting when we talk about cache coherence. So if you're looking at a uniprocessor, this seems like a fairly arbitrary design decision. But when you look at multiprocessors, this becomes a little more important. So inclusive means that every one of these is a strict subset of the larger going out. These properties are not uniform. So you will find that in every case, the main memory is a strict subset of the total mapped memory, at least logically. The caches are a subset of the main memory, but the relationship between the L1, L2, L3, potentially L4 caches and main memory, or even with respect to each other, can vary, right? So non-inclusive, which is Intel's model, is that when I bring something in, I will bring it into every level along the way, but my evictions are independent. Right, so I don't have that subset property. I don't hold it. I don't enforce it. Right, so I could evict something from my L2. I can still have it living in my L1. Again, at this point, not a big deal. When we go then to try to figure out how to do cache coherence, and we need to find where all the copies of something might be, right? And inclusive, it's very easy. If it's in any of these outer layers, it must be, like I can figure out where it is in the inner layers as well. But okay. Oop. Okay, how do we manage this all? Time. Yeah, we get time. Plenty of time. Okay, so the registers, moving between registers and memory is entirely managed by the instruction execution. So effectively the compiler, or if some assembly programmer wrote it, the programmer. The caches are almost entirely hardware managed. There are a very small number of control instructions that can do, say, cache flushes, or other synchronizations. But this is almost entirely a microarchitectural feature. And again, this occasionally comes back and bites us for things like Spectre and Meltdown, right? Because there's no visibility to what the cache state is or is not. So that's good from a hardware design perspective. It's a nice decoupling, right? That abstraction lets you build multiple versions of it that happen to be reasonable to get good yields on without having to bother to have everyone rewrite their code. But it also means that you might get arbitrary state changes on wrong path code, which can be mined for side channels. There's also a memory controller here. So if you're looking between caches and main memory, or caches and caches, so when you get to the edge of the chip and you actually need to go to memory, memory has a fundamentally different protocol than your on-chip interactions. So cache to cache, I just say, I need this address. You give me the address. Great, do a block transfer. Memory, you're actually sending a series of commands. Anyone who wants to look at like a DDR5 standards, right? You can look at the series of JDEC standards for that. So you say, okay, well, I want to open this page, activate this row, activate this column for a burst length of, it's more complicated, right? So the memory controller is a non-trivial piece of hardware that actually does scheduling of understanding how many physical memory devices you have, what timing constraints they have. So all those numbers when you buy your DRAM, right, are actually about the physical timing constraints. And the memory controller has to negotiate and then obey them, issuing a series of commands over a more complicated protocol, which allows you to basically interface with commodity hardware that was not co-designed with your logic, right? So the good news, the cache protocols internally are simpler because all the caches were designed at the same time by the same people. Whereas talking to memory, memory was designed across a common standard that everyone agrees to, which means it's simple to use anyone's hardware, but it's also a little less lean. Right? You have to generalize. If you're going between memory and disk, congratulations, you've already lost the memory wars from a processor perspective. Again, if you're into databases, you're like, no, this happens all the time. So this is just my normal. But if you're looking for high performance computing, a different world. This is handled via virtualization because your ISA has no idea how disks work. Right? That is a detail that is almost certainly not encoded into your ISA. Has very, very limited understanding of how any external IO devices work at all, other than that they can register their existence and you can kind of sort of talk to them some ports. But yeah, your ISA has no idea how disks work. So that is basically left up to software to figure out how that works. And it's software's job to put things into the main memory so that the rest of your software can actually access it, via a bunch of exception handling. Right, so again, one of the more common non-program terminating exceptions you will have is a page fault, a virtual memory exception. Right, virtual memory exceptions happen, and then there is basically hardware acceleration of this. Again, IBM in the 1960s, which explains some of the oddities of the naming, which will help you avoid having to do the entire walking of the virtual memory system every time you want to access anything. And remember, every instruction has at least one memory access because every instruction has to get the instruction, right? So you are doing a lot of virtual memory operations, right? So you're going to average something like 1.3, memory accesses per instruction, right? So you need to actually make this fast. in a system that is not running on bare metal, or else you will have problems. Right. Other movement, yes, there's also user control stuff, files, maps, etc. We're not going to worry too much about that. Take an operating system class or so forth. Okay, so terminology, blocks, frames, lines. So block or line is the unit of transfer. A frame is where you would put it. But block and line are going to be used completely synonymously. For historical reasons, with memory, a block becomes a page. Don't ask. Again, probably the answer is IBM in the 1960s. But so if you're taking, say, this and an operating systems class at the same time, and you're looking at some of the caches, and you're like, well, why do we call it a block versus a line versus a page? Reasons. Nothing deep going on there. Okay, so this is the unit of transfer or presence, right? So a given cache layer has a particular block or line size. The word line actually does help you perhaps understand the physical layout. They are all going to be on some common word line physically, usually. Right, that's at least how they used to be represented. I'm going to light up all these bits at once. That's the unit of access as well. Hit rate, the fractional memory accesses that are found in a particular level of the hierarchy. So we talk about the hit rate per your L1, your hit rate in your L2, hit rate in your L3. Just for completeness, higher hit rate is good. Lower miss rate is good. Right, putting the fires out, good. Putting things on fire, bad. I say this because I've graded too many exams, and sometimes people optimize the miss rate by making it go up. Don't ask. It it does happen. It does happen. But just to remind everyone, we want to hit in the cache, right? Hit in the cache is good. Okay, hit time to access that level, right? So there are two components then. I have to actually get the data. I have to actually then figure out whether or not it hit. Again, if you're looking at something like your L1, these are mostly going to be pretty similar in size. If you're looking at something like your L3, you may be able to figure out whether you hit or miss well before you actually can get the data back. Because the total size of the metadata structures that you need to determine hit and miss, your tag array, are going to be much, much smaller than your data array, right? So there are various optimizations that you can look at where you can actually, in parallel, try to access the block. If it is there, determine the hit and miss, even before you've actually gotten the block back, right? If you can determine that it's a miss, you can initiate the miss process to go up to the next level of the cache and ignore whatever came back because it's wrong, right? So there are games to be played there. And in particular, the more that these diverge, the more that you want to reorganize your metadata and your data separately within your caching system. Okay, miss rate is just 1 minus hit rate. Miss penalty for a level is the average amount of time that it takes to replace a block in that level with the corresponding block from the rest of the memory hierarchy, right? So if I've got something that's missing, all the way to main memory, right? Then I'm going to access my L1, it's going to miss. I'm going to access my L2, it's going to miss. I'm going to access my L3, it's going to miss, right? So that miss penalty for my L1 for that particular access is all of the time that it took to get out there and come back. Yes.
Do we need to remember that entire sum?
No, so two things. We'll revisit the formulas here when we go over AMAT for multi-level cache hierarchies in quite a bit more detail. Later, we're going sort of data path first and then coming back to the memory system. But just remember that these are sort of the things that we are concerned about for now. We'll come back to actually doing problems based on this after we've gotten some more instructional level parallelism going. So yes, you don't have to remember all of this now, but do keep in mind that these are the things that we are concerned with. And again, our assumption on a good cache hierarchy is that your hit time is going to be much, much less than your miss penalty. This is also one of the reasons why we don't have like an L7. Right? So as your cache gets bigger and bigger and bigger and bigger and bigger, it gets slower and slower and slower and slower to access even when it's a hit, which means that at some point, if the difference between the hit time and just going and getting it from memory gets too small, unless your hit rate is 99% or something, it's actually a bad idea to have that additional layer of the cache. It'll actually make your machine slower, right? So if 50% of the time I spend 75% of the time it would have taken to just go get it from where it actually is, for sure, looking to see if it's there locally, right? It's not a good trade-off. I shouldn't build it. Right? Okay. And to know if it's there locally and do anything useful with it, right? The questions we have to answer in hardware, right? How do we know if we have a given piece of data available? And then if we do know that, right? If the metadata tells us it's there somewhere, where is it, right? Some of this, for practical reasons, we're just going to assume some fairly simple mapping functions, because again, I need to resolve this in hardware and quickly. Again, if you look at how you build a software cache, right, you do things that are a little more interesting, right? Your software caches tend to be highly associative. They can have some interesting indexing functions. The replacement can be sort of arbitrarily deep and complicated and look at lots of features of how something is being used. In hardware, I need to respond in a couple of nanoseconds. So I say, oh, I look at your address and I put you here. And if you're there, you're there. If you're not, you're not. And if you've been used recently or other sorts of things, something I can determine in a small number of bits very, very quickly, right? We're not going to be optimal, but we're going to try to make the access fast. Okay. So obviously, if my cache is, say, 64 KB, and one of these particular places within it that I'm mapping is I've only got a few thousand sets, and my total memory space is much, much larger, right? Many, many memory blocks will map to the same physical frame, right? So any particular place I'm looking could host a very large number of distinct blocks in memory. So I'm going to need to uniquely identify them with enough data to figure out which one is or isn't actually there, right? Pretty straightforward, pigeonhole principle, right? If there are, billions of blocks and then only thousands of frames, I need to figure out with enough data which thing is currently in this frame right now. Okay, we can just use the upper portion of the address for this. Are there other things you could do that would also be reasonably fast? Yes, you can throw some XORs in there if you want to sort of spread the space out a little bit for a few reasons. If any of you have looked at recently proposed security primitives for avoiding cache-based side channels, not that I would expect you to have done so, but you never know. There are certainly some things here to play with the set index that have been proposed. But again, the latency on this can't be too high. Okay, the three C's, and we'll get to the fourth C later in the class, right? There are some well-defined reasons that your cache didn't work for you, right? So caches are a demand-based structure. If I have not asked for it, it will not be there, right? So compulsory misses are a data item you looked for isn't in the cache because you have never asked for it to be there. So it's not there, right? There's not really a whole lot you could have done for it. The cache isn't supposed to work that way, also known as cold start, misses. Okay. So the first time you access a block, yeah, there you go. In general, for long-running programs that have any locality, these are not where most of your misses come from. You can increase the block size. It's a form of spatial prefetching. We'll look later at actually explicitly having prefetchers, right? So if you have an access pattern, right? Let's say I'm striding through the column in some multidimensional array, right? I can actually figure out where the next axis is going to be. I could start fetching that in parallel with my current computation. There are going to be some back pressures on that, right? My accuracy is going to be a back pressure. I have to actually store the things that I'm prefetching somewhere. So capacity back pressures, timeliness, et cetera. Bandwidth, if I'm missing to main memory to supply something I might not ever actually access, could be pretty bad. But there's some things I can do if I'm worried about data I haven't touched yet. Capacity, my cache might just be too small, right? If my cache is substantially smaller than my working set, some of my misses are just going to be, there's no reasonable organization of my cache under which I could access this and then access it again and expect it to still be there, because in between this first and second access were 4 billion unique accesses to different blocks. It's not going to be there, right? I've got too much stuff. It doesn't all fit locally. I'm going to have to miss sometimes, right? Now, if you are building something for some particular workload and willing to spend the budget, maybe increasing the cache size fixes this, right? Cache sizes and performance have step functions in them. They are not nice and smooth and linear. The difference between a 33 KB working set in a 32 kilobyte cache and a 33 KB working set in a 64 kilobyte working cache might be like 10x. Because you turn to every something that might be missing entirely and hitting in the L2 is something that's hitting entirely in your L1. Right? This is expensive, doesn't always work. Limitations on how big you can make your cache and have it still be fast. And then finally, if it's not compulsory, it's not capacity, and you still missed, then it's conflict, right? It's a policy-specific organization of the cache decision, right? So if I could have built a cache with full associativity and reasonable replacement policy and it wouldn't have missed, right? But it did miss, then it's because the way that I built this cache, right, has limitations on where the line could be, what it could have replaced, right? Then that have caused it to be evicted before I came back to it, right? So a simple idea here is if I have a two-way associative cache, and so i.e. in every set there are two places I could put a block, but my access pattern keeps accessing A, B, C, D, A, B, C, D, all in that same set, right? I'm trying to fit 4 things in 2 spaces, right? It's not because there are only 4 lines in my cache, right? My cache might be much, much larger, but if I keep trying to put all the things in the same spot, well, this is a local problem with the organization of the cache. That said, reasonable caches have to make these decisions because I don't want a full associative 64 KB cache. That's going to be ridiculously energy inefficient and slow. Yes.
So like from the computer's view, like how does it distinguish between capacity and conflict, or is that like the constant conflict?
Right. So these are ways to analyze why you had a cache miss. Your performance counters don't actually report these. Oh, right. Okay. So if you're looking, why did I miss? And you can say, well, you might have missed because you never asked for it, so it's not there. If you have asked for it and it's not there, it could be that your size of your working set exceeds the size of your cache. Okay. Right. In which case it's you don't have the capacity, you would need a bigger cache. If the size of your working set is smaller than your cache, but you're still missing, and you have accessed it before, right, then you would classify it as a conflict miss. It's an organizational property of your cache that caused this miss. So these are analysis tools.
So these would all be things you would like use in retrospect.
Yeah, you use in retrospect, you would measure these, and they would help you either change your algorithm or redesign the next version of your cache. Yep. Okay. 7 minutes, plenty of time. Okay, so impact on CPI is fairly straightforward. Memory stalls, well, CPI, we can just add them, right? So if you think about this from your, excuse me, you can break this up into some smaller pieces. So for most of this class, we're going to mostly ignore this part, the write stalls, because it'll turn out that buffering usually fixes this. At least for most of the designs that we're going to be looking at. But if you want to understand how things work all the way down, then writes can cause stalls as well if they're accessing memory. But a lot of the writes will be buffered locally. Reads and writes are going to be radically asymmetric because for a read, I don't have the data, and I need the data to do any work. For write, I have the data, I just produced it. It just needs to make sure that any subsequent read to that same location gets me the right value back. So buffering works just fine, right? So I can hide a lot of the latency of writes in real programs. So we're mostly going to focus on read stalls. If you actually want to build a cache simulator, then yeah, you do need to worry about some of these write cases as well. But the vast majority of your stalls in a memory system are going to be on the read side, assuming that you have any reasonable sized provisioning for your write buffer. Okay. You can have write through or write back caches. We're mostly going to be living in write back land because for modern timing and efficiency reasons, you don't want to be trying to, let everyone know about every update to memory you've ever made. If both your L1 and your L2 are private, you might still be sending some of this data on to your L2. You could do a write through L1 to L2, but everything later than that is definitely write back. Right? Imagine that you had write through to main memory. Right? Then every time I do I++ in unoptimized code, it's doing a main memory write. No, you don't want to do that. So most things are going to be write back, but write through is still certainly something that can be there. Okay. So one thing to also take into account is that because of the memory not scaling as fast as your core, in particular, if you look at, say, an off-chip memory, an off-chip memory just has a fixed amount of time that it takes to access. So if I have the same DDR5 DIMM, and I have two different processors with different clock rates, the relative pain of going to memory is worse for the one with a higher clock rate. Right? So or if I have again one with a lower base CPI for its the more efficient pipeline, because the memory parts have a bunch of fixed terms hanging off the end. Right? So basically, if I have a one-level cache, right, no matter what else I'm doing to my design, this 100 sort of just stays there. Right? But currently, this is expressed in cycles, but I really want to think about this as being the result of reducing nanoseconds over nanoseconds per cycle to get the cycles, right? So that base time is going to, yes?
You said the memory speed is unlikely to improve with fast force. You might turn to innovation or what?
There are a bunch of fundamentals in both physics and tech that prevent that. Moving across a wire trace that is several centimeters long is going to be slow no matter what you do. Even if I were to switch to like off-chip optical interfaces, it's still going to be slow to drive a big signal off the chip and on the chip. And the density and scale that we're accessing at. So basically everything that's living at the end, and this is a one level cache, it'll get deeper as we go further. But you have these fairly large terms that are sitting off the end, and they don't scale, right? So your cache access time, your SRAM for your L1, at least mostly is scaling to some degree with your core clocks. But the further out you go, the bigger you're trying to make these arrays, the more that you're going to look at some sort of effectively fixed latency of access that's mostly, say, wire dominated. Right? It doesn't scale with the transistor technologies as much, and then that's going to limit how much you can deal with. So if you're looking at real CPIs, main memory accesses, even though they are rare, because they're so expensive, end up being actually a fairly large contributor to overall CPI. Okay, so again here, with and without, right? Even if you had a base CPI of 2, right, and a 2% die cache miss rate, a 4% decache miss rate in 100 cycles. And again, we already showed you that 100 cycles it would be very, very short, right? If you're going to main memory, you've more than doubled your CPI, right? Even once you play out the entire memory hierarchy and you try to prune this down, this weight here is going to be one of the bigger weights in your overall CPI equation. And so again, if you had an ideal CPI that went down, you go to superscalar designs, going to have a CPI of less than 1, right? And the main memory access time, right, is still stuck, right? And if the decache miss rate goes up, guys, let me tell you, your decache miss rate is decache miss rate of 4% is how should we say optimistic? unrealistically good. Yeah, so for a lot of your time is spent. Again, the thing to keep in the back of your mind, right? All this stuff on chip local is fast. Adders are fast. You don't worry about how slow an adder is. Your time in your program is mostly going to be spent in memory access and I/O. Okay. What do you name that? So much time. Okay, we only have 1 minute left, so we will start off on Thursday with AMAT before going into program dependence graphs, and so starting to get some new material. So we're just about through a couple more slides of review, and then on to everything new. I'll see you Thursday.